Right. Hello, everybody. Good afternoon, and welcome to another class, Wednesday afternoon physics class. All right. So today we're going to start a new chapter in our book, and that's going to be a chapter that will kind of be connected to the previous chapter. So it's about light, and it's going to be about lenses, which are actually very, very similar to mirrors in a way. And so let me see. Oh, I forgot to post a link in Google Classroom. Oh, really? Shoot. That's a bummer. That's actually a bit tough. Can you share that link with the class? I thought I did. I thought I shared the link. Are you sure? Wait, so how'd you get on here? Did you just like go to my YouTube channel? Is that what you did? Let's see. All right, let me see if I can real quick find that. All right. Anyway, so I'm just going to talk a little bit. So I have graded like half of your tests. I haven't graded all of them. And I'm going on to the stream. Look at that live stream. No, that's my chemistry class. Here we go. You're right. And I was having problems with the safe YouTube thing today. It wasn't working for me. All right, anyway, let me live stream now. And let's find, what's my link? My link is right over here. And I'm going to put this. Okay, thanks, Adam. I just put the link into Google Classroom, and then, yeah. Sorry about that. Thank you for telling me. Good that I got students that can figure these things out and get on, even though I didn't post the link. So sorry about that. And Hannah's also here. Hey. And so you shared. So hopefully you guys shared the link also with, whoever else is in the class. I know that not everybody even shows up, but look at this. We have 6 people up, so that's about as good as we ever get practically. And there'll be a few more people coming, and I know people will check it out later. So I'll update the link later, and I haven't put the homework up yet. I don't know. I can't even keep track of what in the world's going on these days. I think I had a student this morning tell me that this is like Groundhog's Day. This whole staying at home and all this quarantine life stuff it's really kind of like Groundhog's Day, which is kind of driving me crazy. But it's got its ups and downs, right? So today we're going to be looking at, what are we going to be looking at? We're going to be looking at light, and we're going to continue to look at different aspects of light. So previously we talked about how light reflects, and now this chapter, so like, let me see, we just finished chapter 13, I think, right? So chapter 13 was all about reflection. We talked about flat mirrors, and then we talked about different types of reflection, specular, diffuse. We talked about curved mirrors, most of the time talking about curved mirrors. Now this chapter 14, which I think we're on chapter 14. I think this is what we're on. Yep, chapter 14 is all about refraction. Okay, so that's the subject for today, to learn about the concept of refraction. So one of the subsets of this is going to be lenses and how lenses work. And they're interestingly quite similar to mirrors, which is interesting because the principle that guides them is very, very different from the principle of reflection. So refraction is completely different phenomenon than reflection, but it's still going to lead to very, very similar situations, so similar diagrams, even similar equations as we already had for our lenses. So in that respect, this chapter is not going to be any harder than the previous chapter. It's going to have some of the same stuff, some of the same kind of math. So hopefully that will start to solidify more as we go through lenses, all the mirror stuff that we did. Okay, and I know the refraction, Snell's law itself can be a little bit challenging at times, but it's not too bad. Okay, so All right, so let's see. We got a few more people. We got 8 people here, so we'll go ahead and get started on the new stuff. All right, talking about refraction. Now, refraction is one of those topics that I've studied numerous times and in various different contexts. And it's one of those concepts that I understand how it works, but it just blows my mind why. And I've heard various explanations as to why it happens, but I think I still don't fully understand the why behind it. So we're going to understand the how, but the why, and you guys can look up various things. Your book is not going to give you a good enough explanation as to why it happens. And I don't think I can give you guys a good enough explanation. I can maybe find some other YouTube videos that might do a little bit better job at explaining why. I know I've seen a couple good YouTube videos that can explain why. And so I'm not even going to attempt to do that. Maybe I'll give you guys a few links because your book doesn't explain the why at all. But basically, the concept of refraction is this, that light, which we previously explained as basically being this wave of particles, right? So you have a wave of particles, and those particles we've called photons, right? And we've said that this wave of particles travels at a particular speed, right? We call that the speed of light. And so c is the speed of light. But it turns out that this light doesn't always travel at exactly the same speed, which is kind of strange, right? It makes sense why some things, for example, we can think of sound. Reconnecting. I think we're back. Sorry about that. Technical difficulties. This is 2020. We shouldn't have so many technical difficulties, especially for YouTube, which is owned by Google, which is like one of the largest companies in the world. I think they're worth $1 trillion. I don't know. Anyway, so what's going on here? This speed of light, which we've thought of as a constant, is actually not a constant. The speed of light can change. So c is not technically the speed of light. It's the speed of light in a vacuum. All right? And so the light goes actually, unlike sound, and so we've talked about sound before, right? So sound travels faster in dense medium. When sound is going through air, it's going to slow down because the air particles are further away from each other. Whereas if you're in a dense material, let's say if you're in water, or even more, let's say if you're in like something like diamond, that sound is going to go super fast, right? Because the particles are so close together, they're going to be vibrating at a much faster speed, and so that sound can go through them much faster. Light is pretty much the opposite, all right? But it's not to the same extent, not to the same extreme. So, for example, for sound, the speed of sound in air is much, much, much slower than the speed of sound through a solid, okay? Much, much, much slower. But light has a kind of the opposite effect. So as light goes through something, or just as light goes through some medium, it slows down. Now we're going to be talking primarily, obviously, about clear objects, okay? So colored objects or dark objects are going to absorb some of that light. We're going to be focusing primarily on transparent or clear objects as much as possible. And we're going to think, okay, even in those clear objects, light is going to be going through them and slowing down, right? And it's going to slow down, and it's even difficult to say exactly, what determines it. Okay, so it's going to slow down some, let's say some in, let's say water, and then more in glass, okay? And then even more in things like diamond. Okay, now you can talk about certain things and say, notice some trends. For example, light tends to slow down more in more dense things, but diamond is actually less dense than glass, and light slows down a lot more in diamond than it does in glass. And it's got to do with something to do with the electrons in the atoms and how they interact with the photons. But again, the exact basis of why this slows down, again, I'm not even going to try to answer it right now because I don't think I can do it justice. So maybe I'll give you guys a link in Google Classroom of somebody that is more of a professional in this kind of realm to give you guys a better explanation as why light slows down through this. We can kind of understand why why sound speeds up in dense materials, but why does light slow down in dense materials? Or why does light slow down so much in diamond? I don't know. I don't think it totally makes sense to me. So I'll let you guys explore that on your own. We today are going to try to figure out more or explore more about the how, okay? How does this work and how can we calculate this light refraction and how can we use it to understand later on how light interacts in things like lenses? So that's going to be our focus today, all right? So I'd like to talk, well, let's look at a specific example here. Let's say air, or so let's say light is traveling through air, and we're just going to give you guys like just a bit of a diagram here. Okay, and so this is going to be this is not going to be a principal axis like it was before. This is going to be just where is a surface between two different media. And so up the top, we're going to say that this, okay, as light travels from air, and let's suppose it's traveling just like this. Now it could be traveling straight down, and if it's traveling straight down, then it's just going to go straight. Right? But when light travels at an angle with respect to a surface just being where two different media are touching each other. So here's air is touching glass right here. When the light actually reaches the surface, and then it's going to bend. And the bending is caused by this change in the speed of light, by this refraction, right? And it's going to bend towards the middle of the object or the material that has a greater index of refraction. And we're going to talk about that index of refraction here later. So this is light traveling from air to glass, all right? And we're going to look at these different angles. This thing right here in the middle, this is called the normal. And I think we've dealt with that before. Basically, it's a perpendicular line. Is perpendicular with respect to the surface, okay? So if you're traveling straight down on the normal, it's going to go straight through and there's going to be no bending whatsoever. However, if we are coming at an angle, the light here, so we're going to call this the angle of incidence, and this is going to be the angle of refraction. The light itself is going to be bent inward like this. Now, you might ask yourself, well, what if it's going the other way around, right? What if you have, let's say, the kind of the opposite situation? What if you have up here is glass, and down here is air, and we still have a normal, right? Just looking at that. And let's say the light is coming in once again like this. And you might ask yourself, well, how then is the light going to bend? Is it still going to bend inward? And the answer is no. Then the light, in that case, the light is going to bend. Hello? Anybody there? Man, Wednesday is just not a good day for this. Anyway, so in this case, when it's going from something like glass to air, the opposite's going to happen. Rather than bending in toward the normal, it's going to bend away from the normal. When it's going from an object that's more dense going to an object that's less dense, like this, okay? And we still would call this the angle. So the angle that is between the light and the normal, right? That's your angle here. And once again, between the light ray and the normal, all right, that's going to be your angle here. So this is your angle of incidence, and this is your angle of refraction. But in either case, the light is going to bend. Okay, whether it's the light's coming from air to the glass, or from glass to air, or whatever. And we can come back up to the previous situation and say, okay, well, what if it was going from air to glass back to air? In that situation, you can probably predict what's going to happen, that this light, you have a new normal here, and that the light is going to continue out going, and it's going to be hard for me to do this exactly, but it's going to continue out going at exactly the previous angle that it was going at, right? And so if we have here a second normal, then this angle right here that is refracted out at, this angle of refraction, is going to be equal to this, I don't know what we call this, we'll just call this angle 2, or angle, no, we'll call it angle 3, is going to be equal to that initial angle of incidence right here. And so that these two lines are parallel. So if it's going in air to glass back to air, the angle or the direction that is going to be, these two lines are going to be exactly parallel. However, you notice that it has skipped down a little bit during this process. And it skips down a little bit, well, because it's going through some other material, all right, which is pretty cool. And so this is, you can study this all you want. You can just get a glass of water, put a straw in it. A straight straw is going to all of a sudden look bent. You can maybe try to go fish hunting with your hands, and you'll probably miss the fish very, very often because the fish is actually in a different place than it appears to be when you're looking down in the water. And so this phenomenon occurs all the time, and you'll see it in water, you'll see it in glass, you'll see it in all kinds of different materials, okay? So this bending of light is refraction, and is caused because light's slowing down, all right? Now let's think about this light slowing down here for a little bit. When light slows down in a material, let's go this way. When light slows down, what happens is that the frequency must remain the same. It's unchanged. All right, well, why is that? Because the materials are not moving at all with respect to each other, okay? And so if this light is, coming or hitting this surface at a certain frequency of, let's say, whatever, 2 waves a second. No, obviously the waves are going much, 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 much more frequently than that. But let's say 2 waves per second. However, if the frequency somehow changed in here, well, then you would have light waves that would either bunch up or spread out, and it wouldn't work. So you need to somehow have the same frequency in this material as the frequency in this material. And so if it somehow bunched up, well, what would happen when the light came out? Well, I don't know. Where would those light waves go? So the frequency must remain the same however it goes. So when the light slows down, although the frequency remains unchanged, well, what has to happen? If the frequency remains unchanged, then the wavelength must change. So the wavelength will shorten. Right? So if this light, if you can remember the whole equation here, right? So the speed of a wave is going to be equal to the frequency of that wave times its wavelength. And so if the speed of light is slowing down and the frequency must remain the same, that means the wavelength must be getting smaller. And so essentially the wavelengths of all of whatever light it is going to slow down as it goes through a particular material. Okay? What else? We can list, and you guys have in your books a table of different indices of refraction. And so we got your first equation for this particular, or first new equation for this unit is N equals C over V. What is this? This N is your index of refraction. Basically, it's something that tells you how much is light slowing down in that material, right? Because C, we've already defined C. C is the speed of light in a vacuum. It's that constant. It's that 3 times 10 to the 8th meters per second. It's that number. It's one of the fundamental constants of the universe, okay? Now V is going to be used by, stands for velocity, but really it should just be speed or something. This is going to be the speed of light in the material or the medium. Okay? And so this number, because the speed of light in the vacuum is going to be the fastest light can ever go, then n is always going to be 1 or greater, right? Let me say that again. Because the speed of light, so c, the speed of light in the vacuum, is the fastest that light can ever go, right? This speed of light in any particular material can never be greater than it, which means that n is never going to be less than 1, right? N is always going to be 1 or greater, okay? So if you have a few things, let's say, the speed of light in a vacuum is going to be c, which means n of air, when light goes through air, this is going to be approximately 1. Now, it's not exactly 1 because air is going to slow light down a little tiny bit. But the speed of light in air is approximately equal to c. So n of air is going to be 1, which means that air doesn't really slow down light much at all. However, water does. So n of water, and I don't remember all these numbers, but I think it's 1.33 or something like that. So when light goes through water, it slows it down a little bit. And then when n goes through, I don't know any of these other ones. When light goes through glass, it's going to slow it down more. When it goes through diamond, it's going to slow it down more. Diamond I think is greater than 2, is 2 point something. Okay, so all these values for the index of refraction is going to tell you how much does light slow down in that particular material. Okay, but this n, this value for index of refraction, interestingly enough, doesn't just depend on the material. So n depends on what? It depends on the material. Generally speaking, like we said before, the denser the material, the larger the value of n, but not necessarily. Like I said, diamond is not a very dense material, but n is very large in diamond. Okay, it's also going to depend on the wavelength of light, right? So how does that work? So basically, the shorter the wavelength, the smaller, the larger the value of n, so that this refraction works more for smaller wavelength light. And so what does that mean? That means that for, let's just compare different colors, okay? So if you're comparing, let's say, maybe blue and orange and yellow, if you're familiar at all with the wavelengths of these, blue has the smallest wavelength, largest frequency, and yellow of these three has, wait a minute, Roy, so I meant to put red down here. Anyway, I got these out of order. So blue, then yellow, then orange, then red. So of these three, red has the smallest frequency, largest wavelength, which means that it's going to bend the least. So for these three, for blue, it's going to be bending the most, whereas for red, it's going to be bending the least. And this principle of an index of refraction that changes based on the frequency or wavelength of light means that you're able to get things like a prism, and you're able to separate light based on this principle of refraction. It means that you're able to get things like rainbows. The whole way that rainbows work is based on light going through droplets of water. And when light goes through droplets of water, it's going to be refracting just like this. Instead of rather this being glass, this would be water, little droplets of water in the air. And you're going to have this little bit of bending. Well, if the bending is more for higher frequencies or shorter wavelengths, then your purple is going to be bending the most, and then next blue, and then red is going to be bending the least. And so that's how you're able to separate light in a rainbow. That same principle is how you're able to separate light using a prism or any other kind of material where you can get some kind of separation of different colors of light when you have white light. Okay, so that's how your refraction is going to be working there. It's going to be your index of refraction is depending on both the material and on the wavelength of light. So let's get down to some math. All right. We have looked at the whole diagram there. Let's actually redo the diagram, and then I'll give you guys the equation. Is Snell's law of when light travels between mediums. And you know what? Actually, I'm going to go ahead and look up our sample problem, and I want to make sure that we get this right. I don't know which material it was for the sample problem. All right. We have, in our sample problem, we have a ray of light of wavelength 589 nanometers produced by a sodium lamp. So very, very monochromatic, so one single color. Traveling through air, strikes a smooth, flat slab of crown glass at an angle of 30 degrees to the normal. All right, find the angle of refraction. Okay, so how do you do a problem like that? What's that all about? All right, so we have, it's going from air to crown glass, and the angle is 30 degrees. Okay, we can do that. We said air to crown, not just glass, but crown glass. And we said it was an angle of about 30 degrees. Okay. That looks like 30 degrees to me. So this is our angle of incidence. And we're going to say that our angle of incidence equals 30 degrees. All right. And we know this is going to bend. And in general, anytime it's going from an object of, or a material of low index of refraction to high index of refraction, that is going to bend towards the normal. So we already know that it's going to bend this way, but we don't know exactly how much. We actually have to do and use an equation to get that. So this is going to be our refracted light. All right. And so in order to do that, we need to look up in the books. And so let's go ahead and do that. And so air, that's going to be about 1. We're just going to assume, so N is about equal to 1 for air. We're not going to worry about any kind of details for that. Let's see. So back a couple. All right, so we have air, right, look at the 1.00029. We're not going to worry about that 29 out there. It's to 3 significant. Okay. All right, so if you look up in the table, you'll find on the table air is about 1, your crown glass is about 1.52, and so now we can actually do a calculation to figure out what is this. So we have your angle of incidence, and we want to know in the problem, okay, what is our angle of refraction? That's the whole idea. So is there an equation? Yes, there is indeed an equation that we use to solve this kind of problem, and that is this. It's called Snell's law. So your Ni, so your index of refraction of your incident material times sine theta I equals nr sine theta r. Okay? And this is known as Snell's law. Snell's law. Okay, so let's go ahead and solve Snell's law for this particular problem, and then we'll be done. All right, so, and you're going to have to use Snell's law to solve a couple other problems. So we have, we know we're solving for your theta r here in this case. So let's just go ahead and divide both sides of the equation by nr. So that's going to give us your sine theta r equals ni sine theta I over nr. Let's plug in some numbers. So ni is 1, right, because it's going through air. And then it's going to be at an angle of 30 degrees. And make sure your calculator is in degree mode. Divide by nr, which we said was 1.00029. 1.52 for crown glass. Let's go ahead and do that. And make sure I'm going to make sure right myself. So make sure you're in, how did I get to be in degree mode? I don't know. I think that happens when your batteries die and you charge them up. It just resets everything to radians. So make sure you're in degree mode by going into mode and switching that over to degrees. There we go. So that's going to be 1 times sine 30 is just sine 30 divided by 1.52, and we're getting an answer. This, you don't even need to bother writing this down because this is not your angle. That's the sine of the angle. So your angle is going to be the inverse sine of that. So you do second sine, you're going to find this inverse sine, and you're going to put your answer in like that, hit enter, and that is the angle. Okay? So your refracted angle is 19.2 degrees. We're going to do everything in degrees, so make sure that your calculator is in degree mode in order to get these right. It's really sad when you get everything wrong simply because your calculator is in the wrong mode. That would be a really, really sad state. So please, please make sure your calculator is in degree mode. The first thing you could do, right? All right, so that's it. We got our angle here, and let's just make some sense of it. Is the angle getting smaller? Yes, right? So when it goes from air to glass, it bends toward the normal. It bends to the middle of the material, all right? And that's that. We're all done for today. Any questions at all? Okay. Any questions? Anything at all? All right, if there are no questions, I'm just going to leave, and we are done for the day. And so I'm going to plan on, don't know if it's going to happen, but I'm going to plan on finishing grading those tests today. So like I said, I graded about half of them already, and so I think I graded about half of them already, and so I should finish the other half this afternoon, and then you guys can check tonight or tomorrow morning. The grade should be in, okay? So Jeremiah, go ahead. What's your question? I'm waiting. Okay, how do you input answer function in the calculator? Simple. All right. So there is something right here where it's like right above the minus. Now I don't know what calculator you have, but mine's right down here. And I guess, let me see. So it'd be nice if I could get this a little bit so you could see the whole calculator. Let me do that real quick. I'm going to bring this up. Okay. So if I'm showing you guys my whole calculator, that's going to be second answer right here. So the second, this minus sign, and that's going to be whatever you have, the previous answer. Okay. So if I want to do 2 times whatever that was, right? Boom, I've got it. Or if I want to do the sign of that, so sign and then second, this minus sign down here, and then boom, I've got it. Okay? Does that work? Now you might have a different calculator, but if you have a TI 80 something, it should be right down here, right next to that. So that's one of the most useful buttons on the whole calculator, being able to use that answer again and again. The other thing that you can always do is you can store things. If you have more than one answer that's important, you go store X is what I do most of the time, or you can do store as, you could do like A, B, C, like store as A, right? And you can do all those different things. So that's very useful too. So being able to use your calculator to avoid any kind of rounding errors and to not have to type all those annoying numbers again and again and again is super useful. So get all the shortcuts for your calculator, use your calculator to the fullest, and yeah, it'll be useful in lots of classes. All right, anything else? Any other questions, guys? All right, I guess you guys got the message that, and I was kind of expecting this to happen because Connecticut has had so many cases of the coronavirus, but I was kind of expecting this to happen, and so we are going to be virtual for the rest of the year, which is, kind of sad for the seniors and all that, but, it is what it is. And, homework will be in facts. Put. Okay, so that's it, guys. I'm going to go ahead and sign out. If you guys have any other questions, feel free to ask. Like I said, I have not gotten the homework in yet. I'm going to do that right away. So I'm going to put the homework assignment in on Google Classroom first, and then I'll put it in Facts, and then I'll finish up your grading. Who knows when I'll be done, but hopefully soon. All right. You guys can always check. So as I grade things, I put them into Google Classroom immediately, but I don't put it back over into Facts until I'm done grading the entire class. Okay, so you won't see your grade up in Facts yet, but you might see it in Google Classroom if I've already graded it. All right, so about half of you guys will probably find it in Google Classroom and half of you won't. All right, so see you guys. Have a great rest of your day, and do pull-ups. This is pull-up month, right? Pull-up May, and today's the 6th, right? And so you got to do 6 pull-ups today. We are shooting for, 31 by the end of the month. We can do it. All right, see you guys.